So imagine this day 50 years ago when every child with leukemia, every adult with leukemia died. The moment they heard the story from their doctor, they were basically dead. That today, 9 out of 10 children that have leukemia are cured of their disease. Now, this is a disease that most people have absolutely no idea what it is. This is a condition that is that starts from very, very early on, such as Lana said. And from birth on, these children have painful erosions, painful blisters all over their body that will never heal. They get infected, and before the era of antibiotics, all these children died of infections. Now, they develop erosions because of the inappropriate repair that occurs after the injury in the skin and in the mucosal lining of the esophagus. They get strictures in the esophagus, cannot eat, so they grow short, and they are ill because of that. Their fingers curl up and fuse together, so they develop deformities and joint contractures. And after this life of pain and disfigurement, after this cruel Hobbesian life, they die of very aggressive squamous cell carcinomas. So this is as bad as it gets. Now, when we came to this, many groups around the world tried to do something about it. We were not the first ones to come with an idea that help is needed. How we differed from everyone was that we thought of this as a systemic disease. We thought, the skin as the largest organ in the body, and all the sites that can be affected by this disease cannot possibly be treated the way the other groups tried, which is treat one wound at a time. So being bone marrow transplant and being stem cell biologists in the lab, we thought that the way to do this is to see whether we can use this amazing drug, which is the stem cell, as to help with this disease. So stem cells are remarkable cells. These are the cells that keep us going. We have about 10 billion cells every single day replaced just due to the regular wear and tear out of these stem cells. So we thought if we combine all these three capacities together, the ability to replace the lymphohematopoietic system, the ability to make the glue, the all-important collagen 7 that is missing in the children with epidermolysis bullosa, and their power to mediate a productive, healthy repair of the skin, maybe we can help these children. So that was the hypothesis, and to test this hypothesis, we went to the mice. We have gotten mice that had been engineered to have epidermolysis bullosa, and we transplanted them with different stem cell populations because we didn't know at the time which ones to use. So this is what a normal skin looks like. This is my skin, so that presumably is normal. You see epidermis on the top layer. This is the dermis on the bottom, and this red band is in fact the collagen 7. This is what people without epidermolysis bullosa will have there. And comparing to this picture, where again you have the epidermis on the top, dermis on the bottom, there's no red band anywhere, and that's why the skin blisters and the erosions happen. So what we did in the clinical trial, we have transplanted children with hematopoietic stem cells, and what we saw is that before the transplant, the skin looked exactly like I showed you before, which is there was no red band of the collagen 7. But a year after transplant, I have a picture now of a 2.5-year-old, 2.5 years after transplant for this child, we see a thick, solid band of the collagen 7 here, which tells us that I'm not saying cure, I'm saying that what tells us this is the most optimistic thing that has ever happened in epidermolysis bullosa, and for that matter, in the realm of stem cell biology that pertains to the what we call extracellular matrix. And being a year-and-a-half-old, this is what his foot looked before, and this is what it looks after. So in fact, we see that it's not just the biochemical evidence that I showed you from the collagen 7 stains. We have electron microscopy evidence as well, but it is the clinical, the functional evidence that this changes the disease. Common things is an injury. all of us will experience injury. It can be, trauma from, fall or car accident, or it can be post-surgical, healing that we need. And all of us probably will experience aging. So all these acquired things that are extremely common, in my opinion, will benefit from stem cell biology and from the ability of these cells to develop, to deliver the healing environment to the injured tissue. So the idea is old, the fulfilling of that idea is new. So in concrete terms, this is what's going to happen, that a particular injury to a particular organ system, such as liver, skin, as in epidermolysis bullosa, bowel, that we would be able, in our lifetime, in our immediate future, in my opinion, we will be able to harness the power of the stem cells, decipher what are the parts of the bone marrow or cord blood or other organ systems, and tailor the specific stem cell into to work in a specific injury. And that's what we are working on. That's where we need your help, because that's where the research is. And as everybody in this room knows, I hope, research is extremely expensive. Yes?
When you talk about the cost of research, can you tell us a little bit more about that, and how long do clinical trials actually take?
Yes, that's a key question. So until I have been involved in this, which is now for about a decade and a half, I had no idea that this is so expensive. So just to put this in perspective, just the things that you have seen would be for a year or so would be in the neighborhood of $500,000.